Hi, my name is Aiden Coleman, and this is my presentation for Physics 1, Lab 3. The objective of today's lab is to observe the motion of a star orbiting a black hole, and in doing so estimate the mass of the black hole. And to do this, we'll use GlowScript to create a computer model that will help us accomplish these goals. Before we go into the computer model, it'll be useful to have some background knowledge on circular motion. Some important concepts are that the change in parallel momentum over the change in time is equal to the total change in momentum over time times p hat. And also it's good to know the change in momentum over time in the perpendicular component is equal to p times change in p hat over change in time, which also is known as net force in perpendicular component. And most importantly perhaps is that we know that the net force in the perpendicular and parallel components add together to give us the overall net force. Just to go over what we're observing real quick, we will be observing a star that has a mass of 2 times 10 to the 30th kilograms orbiting around a black hole, whose mass we do not know. But now we'll be watching a video of the star orbiting the black hole. As you can see, the results from the computer model show that the estimate of the black hole's mass is around 7.4 times 10 to the 33 kilograms. Now I'll be showing you how I modified my GlowScript code to estimate the black hole's mass. Showing the modifications I made to my GlowScript code in order to estimate the black hole's mass. For P initial and P final, we take the star's mass and we multiply by V initial and V final respectively. And then to get the change in velocity and the change in momentum, we just take V final minus V initial and P final minus P initial. And then dp dt, we just take change in momentum and then divide by the change in time. And then F net is equal to dp dt because of the momentum principle. To get p hat, we take the initial momentum vector and divide it by the magnitude of this initial momentum. And then to get the difference in the magnitude of momentum over time, we take the magnitude of the final momentum and the initial momentum, we subtract them, and then we divide it by the change in time. And then to get dp dt parallel, we simply take this value we just calculated and multiply it by p hat. And then F net parallel is the same as dp dt parallel because of Newton's second law of momentum principle. And then since we know that F net parallel plus F net perpendicular equals total F net, then we know we can get perpendicular dp dt by just subtracting parallel dp dt from the full dp dt. And then also with Newton's second law, we know F net perpendicular simply equal to dp dt perpendicular. Now, since we know all this, we can estimate the black hole's mass simply by rearranging the gravity equation of g_mm over r squared just to solve for the mass of the black hole. So once we do that, it'll give us our estimate. And then if we move down here to the arrows that will be represented in our computer model, we simply want to set the position to all of them. We want them to be emanating from the star, so we set it to star dot position. And then for the axis of the arrows, we simply want to multiply the arrow scale by the net force, whichever component it might be F net parallel, F net perpendicular. We just set it to that. And then for the arrow scale, it's set to a number so that it can appear on the computer model without being visually confusing. Now for the question, what if the black hole was swapped for another black hole that has a different mass that's unknown, and how could it be calculated? In the computer model, we don't know the mass at first, and we actually end up estimating it through the velocity vectors it gives us initially, and then we use it to find force, and then we also know the position, so we can use the radius to plug it into the gravity equation to find the mass of the black hole. So if the mass of the black hole was changed, as long as the code given to us updates the velocity vectors, we should be able to go through the same process and make a new estimation of the black hole's mass. Now for this discussion question, we'll discuss how net force and its parallel and perpendicular components are different from the rate of change in momentum and its parallel and perpendicular components. And the confusion here is that the values are the same. You'll get you'll get newtons for either one of these forms, but the concepts behind them are slightly different. Change in momentum over time is caused by an object changing in velocity over time, but the concept of net force is based around an interaction between two objects that does bring about this change in velocity.